Welcome dear students. So myself Dr. Ajay MLT from HNB Gadwal University, Srinagar Gadwal again welcome you in our series of lecture on novel degraded systems. Today we'll be discussing nanotechnology and nanoparticles. We'll be addressing the lecture or we'll be addressing this topic in series of two lectures. In two parts it will be there. So let us open up our discussion on the nanotechnology, which is the future, which is the current and the future of the science. After completing this lecture, you will be able to identify the importance of nanotechnology, enumerate the properties of nanoparticles, and prepare the nanoparticles. We'll be covering this lecture under the heads concept, importance and origin of nanotechnology, then properties of nanomaterials, and then methods of preparation of nanomaterials and nanoparticles. Nanotechnology is the creation of functional materials which have a specific function, devices and systems, functional materials, function devices and functional systems. Through the understanding and control of matter at dimensions in the nanoscale, from 1 to 100 nanometer, where the new functionalities and properties of matter are observed and harnessed for a broad range of applications. Nanotechnology is a cross-sectional technology with influence on almost all industries, and it enables new product properties and is leading to and will lead to new applications in attractive market. Now, what is the nanotechnology? Actually, this is the manipulation of the matter at the nanometer scale, 1 to 100 nanometers, to create the novel structures, novel devices, and novel systems. Three things: novel structures, novel devices, and the novel systems. Now, let me give you a brief history that it was there in the late Roman 4th century AD. This extraordinary cup which you are seeing here, okay, which you are seeing here, it is the complete example of very successful type of nanotechnology. It's a type of glass known as dichroic, which changes the color when held up to the light. The opaque green cup, this opaque green cup turns into this glowing translucent red when light is fallen on it. The glass contains tiny amount of colloidal gold and silver, and this is responsible for this optical activity. And this is the actually the you can see that from the late Roman 4th century AD we are using it. Now we move to the history of nanotechnology. 2000 years ago, sulfide nanocrystals used by the Greek and Romans to dye the hairs. In the 1000 years ago, gold nanoparticles of different size used to produce different colors in stainless glass windows. In Iranian sculptures and Iranian technology, the people used to prepare these kind of glasses. At 1959, there was a very nice statement where that there is a plenty of room. There is a plenty of room at the bottom. There is a plenty of room at the bottom, as you can see here. Okay, by R. Feynman. Nanotechnology, Taguchi used the term first time. The nanotechnology, this term. IBM developed the scanning tunneling microscope. And thereafter, you can see that IBM logo was made with individual atoms in 1989. The carbon nanotubes were discovered in 1999. Nanomedicine, first nanomedicine was that book was by the R. Fetus. And in 2000, National Nanotechnology Mission was launched. And at this time several nanotechnology initiatives and the nanotechnology projects are going on in Indian scenario also, apart from the global scenario. Now, what to speak of molecular nanotechnology? It is intersectional, it is interdisciplinary, it is multidisciplinary topic, multidisciplinary field of research which involves physics, chemistry, biomedicine, pharmacy, engineering, and put together the nanotechnology has got the various application which is affecting the the quality and affecting the current status of the that particular science. Nanotechnology key factors: particle size, morphology, degree of crystallization, crystal structure, and chemical composition. These are the five major key factors on which the nanotechnology revolves around. The key factors are, as far as the driving force is concerned, chemical kinetics and thermodynamics are the two important driving forces. Now let's see some basic rules and basic things. These are just the representative figures I'm showing you. That smaller means nearer and quicker to connect. Two big football centers and the centers of two nuclei. It means nearer it is, quicker it is to contact. Smaller means more reactive. Sugar crystals versus sugar powder, you can see that the crystals may take most time, may take the more time as compared to the amorphous form, simple powder form. They dissolve quickly. Just it's simple, it's a representative figure. Okay. So smaller means more reactive, higher contact point will be there, so the reaction will be more. But smaller means higher surface area. I would like to add on for the previous slide also that however, it depends on the nature of drug, that whether you are, if decreasing the size, the solubility will increase or not. And the nanoparticle especially, this is entirely different scenario. But in general, we have seen, it was a representative thing only, just to have you the concept. But now we are talking about the surface area. Let's see this example. We have a cube of a dice, a simple cube, you can say 1.7 centimeter side each. What we are going to do, we are going to cut it 3 times, horizontally, vertically, and transversal, and repeat this cutting for each cube 24 times. What you will get? You will get the cubes which are of 1 nanometer scale. The number of what number of nanometer the cubes you will get, what surface. You can cover the entire standard football ground with this layer of cubes which you have obtained by this process. Means enormous surface area they are having. Their surface area to volume ratio is very high. This is the peculiar phenomena. This is a specific phenomena for the nanoparticles, and the nanotechnology has got this beauty of giving the enormous surface area. Now let's discuss the properties of nanomaterial, because if before going to know or before going to address the preparation methods, we must know what are the properties of nanomaterials, because these are the properties which make them applicable for various industries, various applications. So we will have to understand what are the unique properties that nanomaterials are having. Why nanoparticles are different? First, let's understand that nanoparticles are different from bulk materials and isolated molecules in various properties, like having the unique optical properties, electronic properties, chemical properties, and mechanical properties also. As the dimensions of the material is reduced, what is happening? That electronic properties changes drastically as the density of states and the spatial length scale of the electronic motion are reduced. The electron confinement is there when you are decreasing the size. Closely related to size induced change in the electronic structure are the optical properties of nanomaterials. Size effects. That size effects are giving the peculiar and fascinating aspect to the nanomaterials. Size does affect. The effects determined by the size pertain to the evolution of structure, thermodynamics, electronics, spectroscopic, electromagnetic, and chemical features of these finite system with changing size. These properties are gonna be changed. Nanoscale size effect. How the nano size particles will or nanomaterials will have the unique property. They will have the unique properties. They will have a unique changes in the physical properties like melting point, chemical properties like reactivity, electrical properties like conductivity, mechanical property like strength, optical properties like light emission. So these properties are going to be drastically changed. Now let's take the example of size effect on the gold particles. As you can see, the bulk gold material, this bulk gold material is of this size. Okay, this color, that yellow color. Gold particles of 30 to 500 nanometer are generally the crimson to blue. These are the two colors from 30 to 500 nanometer if you move. Now, when we are decreasing the particle size to 3 to 30 nanometer, this color of the same gold is now red and metallic transparent. While if you go to the 1 nanometer scale, then it will be, the gold cluster will look like this orange non-metallic one, while in the angstrom level it will be colorless. 1 angstrom level it is colorless. The properties of a material depend on the type of motion in electron, or type of motion of its electrons, and what electron can execute, which depends on the space available for them. Electron confinement is happening there. Thus, the properties of a materials are characterized by a specific length scale, usually on the nanometer dimension. If the physical size of the material is reduced below this length scale, its properties change and become sensitive to size and shape. So the electron confinement is basically the responsible for these properties. Melting temperature. When we go to the nano size, the surface energy increases, and this increase in surface energy increases and melting point decreases. Say for example, 3 nanometer of cadmium selenium nanocrystal melts at 700 Kelvin, while in the bulk the same melting point is 1678 Kelvin. Can you imagine the huge difference? Yes. Melting point, if you say for the gold, the melting point of gold particle decreases dramatically as the particle size gets below the 5 nanometer. As you can see, say for example for 10 nanometer it is around 1000 degrees Celsius, while for 5 nanometer it is 800, or and while you go for the 3, while you go for the 2, it is just 500 degree Celsius. So you can imagine that how drastically it is. Drastical decrease is there. The dip in melting point is there depending on the particle size after the 5 nanometer scale. Okay, you can see the change. An electron confinement, we can see from when the bulk material is reduced to in size, its orientation of the electron movement is confined from 3 directional to 2 directional to 1 directional and then 0 directional, and that's why it is called bulk, quantum well, quantum wire and quantum dots, because the quantum confinement, the electron confinement is there. Depending on these factors, depending on this electronic confinement, the properties get changed, and ultimately this quantum dot is the complete confinement of this electron. There are different types of nanomaterials. They may be nanopowder, nanotube. Nanopowders, they are building blocks less than 100 nanometer in diameter. CNT, they are tiny strips of graphite which are sheet rolled into tubes a few nanometer in diameter and up to 100 of microns in size of length. So micron size length and nano size diameter. Okay. These are the various types of nanoformulations. We can prepare in the nano size. If we say that we can prepare the micelles, we can prepare the we can prepare this micelles. Now, what are the advantages of polymeric nanoparticles? Increase the stability. We can increase the stability with the help of the nanotechnology of any volatile pharmaceutical agents, easily and cheaply fabricated in large quantities. Significant improvement over the traditional oral and IV methods of administration for increase in effectiveness and efficiency. It delivers a higher concentration at the site of action or the desired location, and it is ideal candidate for cancer therapy, delivery of vaccine, contraceptives, and delivery of targeted antibiotics. We can design different polymeric systems for polymeric nanoparticles for these various therapeutic actions. Polymeric nanoparticles, they can be easily incorporated into other activities like the drug delivery, tissue engineering, etc. Now we are moving to preparation of nanomaterials. What kind of approach we may be? We may have the two approaches, bottom up approaches and top down approach. So bottom approach means from building blocks we are preparing nanoparticles, okay, and top down means from the bulk we are cutting it up to the level of nanoparticles. So these are the two basic approaches, okay, and different method may be there for bottom up and top down, as you can see here. So methods of nanosynthesis, they are basically, if you classify physical and chemical, they are the two methods. In physical methods, carbon arc, laser ablation, vapor trapping. In chemical methods, sonochemistry, these are the sonochemistry, microwave synthesis, hydrothermal methods, microencapsulation, sol gel methods, wet chemical precipitation, wet chemical co-precipitation. These are the methods by which we can prepare the nano materials. Nanoparticles preparation methods, as we have discussed, that they may be bottom up and top up synthesis. This is the flow diagram which we have taken from this reference, which is of Creative Commons. So you can also adapt it. So bottom approaches, these are the approaches: spinning, template, support, plasma. I'm not going into the detail of each and every technique. We will be discussing, we will be focusing our discussion on the biomedical, or you can say pharmaceutical nanoparticle only. So their top-down synthesis may be done by the mechanical milling, chemical etching, sputtering, laser ablation, and electro explosion. Okay. As far as the core shell nanoparticle is concerned, to attach the various active functional, the core shell nanoparticle can be developed. They may be developed as organic, inorganic, or the biomolecule can be developed at the core shell nanoparticle. In the surface of nanostructures, we can put these biomolecules, and coating these nanostructures may be coated by another material to form a core shell structure, and they are called core at shell. So core is you can say colored and fluorescent. It may be it may be magnetic, drug reservoir, empty. Okay. Now moving to the nanoparticle synthesis. In the nanoparticle synthesis, the most important and most pioneer, you can say the very pioneer study was in 1968 by the Stober, in which silicon nanoparticles were synthesized by the addition of precursor tetrahydroxysilane into alkaline ethanol. As we can see, the synthesis proceeds through hydrolysis condensation reactions. Ammonium hydroxide we are adding to this absolute ethanol, and the TUS with the stirring at 3 to 30 hours, the nanoparticles are achieved. So this Stober process is very popular in the nanoparticle research. It's a very simple preparation. It provides a very simple preparation methods, and spherical non-porous particles of diameter ranging from 20 to 100 nanometers can be achieved with this. And narrow size distribution there, polydispersity is very good, uniformity is very good there. Okay, so easy surface functionalization can be done with silanes. Okay, so now moving to the methods in pharmaceutical nanoformation development. It is not a cup of tea of everyone. It is not a cup of tea of everyone. I would like to emphasize that developing nanoparticles is a very typical task. For the synthesis, sometimes it's very simple, but when you are especially preparing for the organic nanoparticles, it is a art as well as a science. You have to control various factors. Inorganic nanoparticles are quite easier to develop rather. Okay, but when you are adding the functionalities there, it becomes a challenge. Okay, for site of action, for desired targeting, for desired localization into the site. So let's see them one by one. Dispersion of drug in preformed nanoparticle is the first approach, and second approach is polymerization. This first approach, the methods involved are solvent evaporation. Okay, they are the solvent evaporation there. Solvent evaporation, nano precipitation, emulsification, ESD, emulsification, solvent diffusion, salting out, dialysis, and supercritical fluid technology. Okay. While in the polymerization, emulsion, mini emulsion, micro emulsion, interfacial polymerization, and the controlled polymerization or living radical polymerization. Okay, these are the technologies which we'll be discussing. First is solvent evaporation method. So what we are doing is similar. These are the in this study, in this method, polymer solution are prepared in volatile solvents. They are prepared in the volatile drug and polymer solution are taken, and their emulsions are formulated. These emulsions are formulated, and these emulsions, the emulsion is converted into a nanoparticle suspension on evaporation of the solvent for the polymer, which is allowed to diffuse through the continuous phase of the emulsion. This ESD is done and freeze drying is done, and then the nanoparticles are obtained. So two main strategies we may have. The oil and water emulsification or the multiple emulsion we can prepare, and then for the with the high speed homogenization, ultrasonification, followed by the evaporation of the solvent at room temperature under reduced pressure, the solidified nanoparticle can be collected by the ultracentrifugation and washed with the distilled water to remove the other additives such as surfactant, finally to produce this lyophilized nanoparticle. Okay, this is the simplest method and the most common method which is used for the nanoparticle preparation. Nano precipitation method. It's a basically it's a also called a solvent displacement method. What we are doing here, that we are taking the organic solution, polymer and drug and surfactant are taken. It involves the precipitation of a preformed polymer from an organic solution and the diffusion of the organic solvent in the aqueous medium in the presence or absence of surfactant. Okay. The polymer, generally PL, is dissolved in water. It is dissolved in water and miscible solvent of intermediate polarity, leading to the precipitation of nanospheres. This phase is injected into a stirred aqueous solution containing a stabilizer as a surfactant. Polymer deposition in the interface between the water and the organic solvent, caused by the fast diffusion of the solvent, leads to the instantaneous formation of a colloidal suspension. Okay, this colloidal suspension, basically it is applicable to the lipophilic drugs because of the miscibility of the solvent with the aqueous phase, and it is not efficient means to encapsulate water soluble drugs. So this was all about the nanoprecipitation method, as you can see. Now the modified version of solvent evaporation method is the ESD, that emulsification solvent diffusion method. In this method, the encapsulated polymer is dissolved. This encapsulated, the aqueous surfactant solution and the polymer solution, they are taken, put together. They are dissolved in a partially water soluble solvent such as propylene carbonate and saturated with water. They are saturated with water. Okay, they are saturated with water, and to ensure the initial thermodynamic equilibrium of both the liquids. Then what we will do, the emulsification will be the next step, in which the oil and water emulsion is prepared, and then the solvent diffusion is done by the polymer precipitation. The purification, cross flow filtration is done, and then after the freeze drying, the polymeric nanoparticles can be obtained. Okay. Now the organic if you go to the salting out effect, it is a very easy method. It is based on the separation of a water miscible solvent from aqueous solution via salting out effect. The organic solution, polymer, drug and acetone we are taking, and the aqueous solution, we are adding stabilizer and salting out agent in water. These salting out agents are like magnesium chloride, calcium chloride, and magnesium acetate, or non-electrolytes such as sucrose. So this oil water emulsion is diluted with a sufficient volume of water or aqueous solution to enhance the diffusion of acetone into the aqueous phase, thus inducing the formation of nanospheres in the last step. As far as the salting out is concerned, it has got the advantages that it minimizes the stress to protein encapsulants, and it is suitable for the thermolabile substances, because it does not require any increase of temperature. So very useful. Disadvantages include it is exclusively only for the lipophilic drugs, and the extensively there is the extensive nanoparticle washing steps are there. So that's why only for the lipophilic drugs it is useful. Now moving to the dialysis, as the name suggests, there is a dialysis membrane. A simple and effective method is the polymer solution is of drug polymer solution. Small narrow is put into the small narrow in this dialysis membrane. Polymer is dissolved in an organic solvent and placed inside this dialysis tube with proper molecular weight cutoff dialysis is performed and against a non-solvent miscible with the former miscible. The displacement of the solvent inside the membrane is followed by the progressive aggregation of the polymer due to loss of solubility, and the formation of homogeneous, this you will get the homogeneous suspension of nanoparticle you will get at the last stage. Okay, so in the dialysis tube, what we are doing, polymeric solution in the organic solvent we are adding this, and in the dialysis, and then after that, after dialysis, it's a suspension is homogeneous suspension of nanoparticle is obtained. Now spray drying method. Spray drying is what we are doing here. You are to the drug solution suspension in polymer solution is atomized with the help of atomizer. In the liquid nitrogen and the frozen nanoparticles are obtained, and solvents can be extracted in the spray drying method. Other method, conservation phase separation, as you have learned in the microcapsules in your previous classes, that with any change in phase separation can be done with either by the temperature change, pH change, salt addition, non-solvent. What will do, protein in aqueous solution, that phase change is done, and with the help of stirring, probe sonication, and protein nanoparticle precipitation is done, and the cross-linking with the help either chemical or enzymatic cross-linking is done to get the cross-linked nanoparticles. So this is the another method. This is and it is common, it is common for the microcapsule, microspheres, and nanoparticle. All depends on this speed of homogenization, or the stirring speed what we are providing. Supercritical fluid method, as we have discussed, it is a very advanced technology. There are two major technologies there, RESS, and one technology is RESS and RESOLV, resolve. In RESS, it is called rapid expansion of supercritical solution. It involves expansion of the supercritical solution in ambient air. Okay, while in resolve, this expansion is into a liquid solvent which is called resolve. Okay, first is RESS, second is resolve. So by this method, the liquid solvent apparently suppresses the particle growth in expansion jet, thus making it possible to obtain primarily nano-sized particles. The high degree of supersaturation accompanied by the rapid pressure reduction in the expansion result in homogeneous nucleation, and thereby the formation of well dispersed particles we can have by this method, either the RESS method or resolve method. Okay. These are two different sub methods of supercritical fluid, anti-solvent method and gas anti-solvent method. So these two methods have also been discussed in the previous lectures. Again, with the use of anti-solvent like carbon dioxide, the supercritical fluid, we can use this technology. Polymeric ionization method, polymerization method. What we are doing, the monomer and drugs that are taken together, and then acidic medium in the presence of surfactant or stabilizer, the polymerization occurs, and then purification step is done, and nanoparticles can be prepared. Okay, so this is one of the methods of polymerization. However, as far as the polymerization is concerned, we have discussed in detail in our previous lecture in developing the other microparticles. These are the references. You can go ahead, some examples, especially these references we are giving. However, there are so many references on no degree systems and this aspect. Now let me summarize what we have learned. As we know, the nanotechnology is the not only the future, it is the current science. Yeah, it is the hot discussion. This is the center point of attraction for the various fields of research, not only the biomedical, pharmacy, medicine, chemistry, physics, engineering. All the scientists of all the disciplines are working very effectively and very with the enthusiasm to develop new structures, system, and devices from the nanotechnology, and the range within the range of 1 to 100 nanometer. The nano size, this nano size is basically the driving force for the change in the properties like physical properties, chemical properties, electronic properties, its conductivity, mechanical strength. So all these properties, including the color, we have optical activity, we have addressed. Okay, the gold film example you might remember. Then there are two basic approaches, bottom up and top down approaches. Then preparation of drug dispersion in formulation. Dispersion in preformed nanoparticles and polymerization are the two basic techniques. In the preparation of drug dispersion in preformed nanoparticles, we have discussed the sub techniques there, like the solvent removal, the EDS, and the salting out. These are the technologies which we have, the methods we are salting out we have discussed. So let's remember these technologies. Apart from this polymerization technique, we also discussed in the microparticles. Also, we have discussed these techniques. So what is required from exam point of view? Defining the nanoparticle. What are the properties or basic properties of nanoparticles? Thirdly, the methods of preparation, the classification, top down, bottom up, and then the two different classification and their sub techniques we must know. You won't have much time if you try to address each and every method, and you are trying to write in sentences. I again emphasize that give your power pack presentation with the help of flow diagrams, ray diagrams, and the concise tables whenever it is required. So we will be discussing the further part of the nanoparticle technology, or nanotechnology, in our next lecture, and we'll be coming back with the characterization and the application part in our next lecture. Thank you for being with us. Hope I have addressed all your queries, and we'll be coming back with the next lecture on nanotechnology and nanoparticle.